let's look at problem 29. I said 28, we'll do 29. This is not a distance rate time problem. Okay, a container has 6 liters of a 40% alcohol solution in it. How much pure alcohol should be added to raise it to 60% solution? Okay. So sometimes a picture helps. The picture here is, have you taken chemistry yet, by the way?
Yes, I took it
Okay.
sophomore year.
Okay. So there's a 40% solution right here. We know that its water level is 6 liters, and we have a unknown level of 100% solution. Okay.
Okay.
And the idea here is that you're going to take some of this 100%, you're going to pour it into the 60%, I'm sorry, the 40%, and it's going to go up. If you've ever had like orange juice and you put water in it, or Gatorade and put water in it, it's the same idea. You're kind of diluting the solution. Here we're actually making the solution stronger because we're going from 40% to 60%. So for the time being here, though, imagine that you dump all of this into a big container, all right, and then the 100% you're going to add in as well. Okay, but you first start, you take all the 6 liters, you dump it into a big one, and then you're going to start grabbing from here. So the general formula here is percentage of the solution times the amount. Okay. So from the first one, you have 40%, 0.4 times 6. Does that make sense? An amount, it means the amount of liquid material.
Yeah. Okay. So
Plus,
yeah.
plus, now it's 100%, and that's 1
Right.
as a percent. And then we don't know how much we're adding in.
So we're going to multiply by X.
Yes. Okay. Now our goal, you can think of your goal as being over here on the other side of the equal sign. Our goal is what percentage in the problem?
Our goal is 60%.
60%. And we know that we're going to have 6 gallons plus however much we add from the other.
Okay.
So for each of these things that we've written, really, really super important here, it was percent, 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 and then the other number is the quantity or the amount. We can think of it as quantity, 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 or volume, quantity. How many variables do you see in this equation?
2.
But they're the same, right?
Yeah.
X and X name. So you've condensed this word problem into just a single linear equation. And you can solve for X.
Okay. And then
These are the mixture problems, if you will. You know, maybe heard that before. I'm just hearing like some uncertainty or like how can it be this simple?
right. It doesn't seem like it should be this simple, but
yeah, well, it is. It really is. Did you guys make tables or something in class?
no.
Okay.
We did draw a picture, but that's basically it.
Yeah. So these mixture problems, kind of drawing two containers is probably pretty helpful to kind of diagram what's going on. But the key is this percentage times quantity, or percentage times amount, or percentage times volume. That's what you're using over and over again. Okay, so in terms of solving this, 0.6 times, I'm sorry, 0.4 times 6, you got to calculate, that's 2.4. You can do it by hand. 0.6 times 6 is 3.6 plus 0.6x. And now your goal is to get x by itself. Subtract 0.6x from both sides. Subtract 2.4. And you get 0.4x equals 1.2. divide both sides by 0.4, and X equals 3 liters.
Huh. Okay. Okay. And it equals 3 liters because
If you divide, you get 3. I mean, you can use a calculator, or you multiply the top and bottom by 10, and you get 12 over 4, which is
right,
3.
right. Huh. That seems very easier than I thought it would be.
So let's look at it. Let's look at it from a different perspective. If you have, let me just restart the problem here. This is kind of an SAT thing that we're about to do, but it's important. If you took 6 liters of a 40% solution and 6 liters of 100% solution, what do you think the final mixture would be?
Um, Probably like a 70%
Yeah,
solution,
70%, right?
right?
So that's if you did 6 liters, and we're not doing 6 liters. Okay. So the question is, well, if you do 3 liters, like, how does that number change? Well, it goes down, right?
Right.
It doesn't go down to like 55. We just proved that it goes down to 60. But the point is like your number is reasonable. Super, super reasonable. Because like 3 liters or 6 liters would make it 70% too big. And 3 liters is closer to that number.
Hmm.
It's just kind of an estimation that's totally reasonable. All right, now let's try 30. It's really, really similar. But these are, students say, I hate these mixture problems, they're too hard. They don't have to be. They don't have to be, because you well, you have the answer. but
Well, yeah,
you can draw a picture here. So the idea here kind of is okay, you got to draw a picture. So we've got a 60% acid solution. Okay, and that's kind of like the one you can pour unlimited amount that you need to. And you're starting with 14 liters of a 10% solution.
Mhm.
And our goal is to get to a 25% solution. All right. So if you added 14 liters of the 60% to the 14 liters of the 10%, it would split the difference. It would be about be 35% solution.
Right.
Do you agree with that? Like the kind of the same logic as the last problem.
Right. Yeah, that would make sense.
And 35% is too big. So we know though the answer is closer to 14 than it is to say 0. Like you're going to add substantial amount because you got to more than double its acidity.
Right. Okay.
Right. And so that kind of just gives you some like, well, is my answer even reasonable? We'll see. All right. So in terms of the equation, I can give you a little bit more. It's the part 1 or the container 1. You're doing this for container 1, part 1, plus part 2 or container 2 equals the together or the combined. That's what we're doing each time. Percentage times volume or percentage times amount equals percentage times amount. So you start with, they say you start with this one, like this one is 10%, 0.1 times the 14 plus
Right.
part 2 is 0.6, but do we know how much we're adding?
No.
No, we'll call that X. Together, they make a 25% solution. And the volume together is what you started with, the 14, plus however much you added with it.
Right.
Percentage times amount, percentage times amount, percentage times amount. That's going to be the key to doing these problems.
Hmm.
Any questions on that?
No.
Okay, so multiply these in 1.4 plus 0.6x equals. So we got 0.25 times 14. You can think of 0.25 as a fourth. Fourth times 14 is 14 over 4, 7 halves. So 3.5 plus 0.25x, like that.
Hmm.
Now we've been working together a
And
while now, Joaquin. Like when you give me that, are you telling me you don't understand? You agree with it? Like, give me some feedback because I can't see you, and you don't need to turn on your video or anything like that. But I'm just sort of asking, like, what does that mean? Are you frustrated?
no, sorry, I was trying to figure it out on my end too, and
Okay.
that's seeming to make sense to me right now. I
Okay. Would you like me to give you more time to work these out before I jump in when we're working them?
uh no, it's
Okay.
okay.
All right. So we have to combine like terms. So we're going to subtract the 0.25x. Subtract the 1.4. Get 2.1 on the right. On the left here, 0.35x. Divide both sides by 0.35. And from here, if you haven't done this in a while, you can multiply top and bottom by 100. So that gives you 210 over 35. 35, sometimes it's helpful to, like, if you multiply 35 by 2, that's 70. Like, oh, that works because 70 times 70 times 70 gets you to 210. Somehow you have to, like, work these numbers out, either building a factor ladder or figuring out what goes into each one, or starting to divide each of them. Like if you divide each by 7, you get down to 30 over 5, and that's 6.
Okay. And we can prove this by just doing the problem back.
What do you mean by prove? Show that it's correct?
Yeah.
Yeah, I mean, you can go back to this line, right? Let me put the arrow here. You can go back to this line to check x equals 6. Like you can say, all right, 0.1 times 14 plus 0.6 times 6, 3.6 plus 1.4 is 5, 14 plus 6 is 20, 1/4 of 20 is 5. It checks out.
Okay. Okay.
So do
Okay.
you want us to do you want us to do some more mixture problems or move on to a different type of problem?
Maybe not mixture problems, but can we just do like word problems in general?
Sure. I thought doing the distance formulas would be good because there's a couple of different types of problems that they have usually. So can I go back to like 24?
Sure. Yeah, that would be great.
All right, so the next kind of grouping of problems, they're all governed by this distance equals rate times time. Distance equals r times t. So we're going to be using that a lot here when we're working these problems. So it says two cars are 510 miles apart and whose speeds differ by 6 miles per hour, and they're moving towards each other. So this is where it's good to have a picture. So let's use, let's say here's Joaquin, here's Matthew, and we're driving our cars. Hopefully we got nice cars. 510 miles apart.
Mm-hmm.
Okay, and we don't know the rate though, but we know, and you can ignore that. So you gotta assign r to one of them. So who's moving faster? Are you moving faster or am I moving faster?
Um, I'm moving faster. I'm an irresponsible driver.
Okay. So We don't know whether, so you're the one that's moving faster, R, okay? And
Okay.
I'm moving 6 miles per hour slower, R minus 6.
Okay.
Now, if you didn't like that, if you're like, well, wait, that doesn't, I don't like that, you could do the following. You could say, well, my rate, Matthew's rate is R, and then your rate is R plus 6. And they do give you the same answer. So there's multiple ways to work these problems.
Yeah.
All right, but we're gonna exclude that for right now. And then the time is 5 hours. Okay, so we both go 5 hours. All right,
Okay.
so now after you've set up this situation, the scenario, you generally now write a D equals RT for each person. Okay, so let's start with you. Let's start with the rate. What is your rate?
Um, R
R. What is your time?
5.
5. So you're R and 5. Now, do you know how far you went?
No.
No. So we're going to call that D1, subscript 1. Is the subscript okay?
Yeah.
Okay. Now we're going to go over to me, Matthew, and same deal. D equals RT for now. Do we know my rate?
R minus 6.
Do we know my time?
5 hours.
5 hours. And do we know how far I went?
Also no.
So we'll call that D2. So the problem with what you have right here is you have D1, R, that's 2, and D2, 3 unknowns. 3 unknowns, 2 equations, that's bad.
That is
You
pretty
have to
bad.
have this, you have to have the same number of equations, as unknowns.
So we only have 2 equations, but 3 unknowns. So we need
Yeah,
another equation
right. And we
or less unknowns.
well, we need another equation. So what we did not use, sometimes you get to this point, you're like, what do you mean? Then you realize you didn't use all the information. We have not used the 510. What does the 510 represent?
Um, both of our distances.
Exactly. So there's your third equation. D1 plus D2 equals 510.
510. Ah,
Do you know
interesting.
D1? Yeah. D1 is 5R. Do you know D2?
Yeah,
R
it's
minus
5R
6.
minus
Yeah, 5 times R minus 6 equals
510.
10. So I'd like you to
Okay.
solve for R, please.
Um, hold on. Let me
If
get
you have
my.
if you have questions, please ask, but I'd like you to try working this out from here and
Okay.
letting me know if you run into any issues along the way.
Um, is it 54?
Okay. So you got R is 54. Now this is
Yes.
a word problem, so we do need some units to go along with it. What are the units of speed?
Miles per hour.
Yeah. So if you're in my classroom, I would be very unhappy if you did not put the units because I don't know what 54 means. And you don't either until you tell me that. It's really important. But the thing is when you're doing math, like for so long, it's like solve for X, solve for Y. So, but like these word problems are very much more important than the ones you've been solving. So it is kind of unfair to you to be like, oh yeah, units, because you haven't been dealing with them for most of the year, but it is really important, really, really important. Okay.
Okay.
Now, the other thing here to pay attention, this truly is like your standardized test question. You got to figure out what they're asking for, and they want the speed of each car. So you have half the answer. And
Right.
what I also don't know if I'm grading you is have you clearly said that this is Joaquin's speed? Like I would want to know that 54 miles per hour is your speed.
Hmm.
I want more specificity. Okay. And then what's the other speed? Matthew's speed here? It's R minus 6.
So 54 minus 6, which is 48.
48 miles per hour. Now here's something else the problem did not ask for, but it's reasonable to ask. Where do we meet?
That's a good question.
Yeah. I mean, if you've ever had a scenario, and I had one this summer where I had my car had broken down, but then it started working again, and I drove back the direction I came, and I had someone coming to meet me, and it was this exact scenario. It's like, well, where should we meet? And I'm like, well, I'm at mile 100. And they're like, well, I'm at mile 80. I'm like, well, we'll probably meet at mile 90, right? Well,
Right.
inevitably, we actually didn't, they went by me, I went by them. And this thing always happens, but we can do better than that, right? We actually can figure out how far you will go and how far I go. Because your distance is your rate times your time. Your
Right.
rate is 54. So
Times 5.
times 5. So you go 54 times 5, which is 270. Okay. And then Matthew, he went 48 times 5, which is 240. Does it make sense intuitively to you that if you went faster, you're going to cover more ground?
Yes.
And it should, yeah. Okay. So that's that's the more like if you and I were building an app that was like, hey, you're starting there and I'm starting there, and we figure out where we're going to meet. Like they don't care about your speed; they care about where you're going to meet. That's what most people want to know.
Right.
And they might be like, well, I'm going to drive at 70, and Matthew's going to drive at 68. Where do we meet? So these are all kind of things that that's real life. Real life is maybe in a textbook problem you just want to know the speeds, but real life is we might actually want to know where that is.
Right. Okay. So in this case, we would meet at mile 240.
Well, that's really an interesting question because we actually don't know where the start and the stop is, which adds more complexity. But let's just say that you were starting at mile marker 0 and this was 510. Okay, we would meet at mile marker 270. But if we didn't start, like let's say you start at mile marker 10, we would actually meet at mile marker 280 now.
Right.
And
Okay.
that's like a scaling issue that you see where you don't know if your scale starts at 0 or 10 or what. Okay, enough about that problem. We could, I could diverge for hours on stuff like this. Let's look at 26. I like looking at the even ones because I know you don't always have the answers to these, but in this case you do. Is that okay? If we move on to this one?
Yes.
All right. A jogger who can run an 8-minute mile starts a half mile ahead of a jogger who can run a 6-minute mile. Okay. How long will it take the faster jogger to catch the slower jogger? So here's the scenario. There's do you want to be the 6-minute or the 8-minute runner?
The 6-minute.
Okay. All right. So I'm the slow one here, and I get a half mile start. I get a half mile start here. That's my distance. But at some point we meet up, right?
Right. At some point.
At some point down the road, we're in the same spot. So that's where the picture, you got to draw the right picture, meaning like uh things match up together. All right. Now, in terms of time, well, we don't know time, but what do we know? What is the 8-minute mile?
Half a mile ahead.
What does this 8-minute though mean? Is that the time or is that a rate?
Rate.
It's a rate. So it's saying that in 8 minutes, you can run 1 mile. Now we generally like things to be in terms of like miles per hour. So
Right.
we have to do a little conversion here. So you can do 1 mile, but how much is 8 minutes in terms of an hour?
Um, 8 minutes is like
So if you go back to chemistry, there's 8 minutes, 60
mm,
minutes in 1 hour. So you have to do this calculation.
8 divided by 60.
Yes, whatever that is.
Right.
All right. And then,
Uh,
but then it's really the reciprocal of that.
so 1/6? No, that's not right. I oh
So
no,
what I'm saying, like in terms of the calculation, it's 1 divided by 8
whatever
divided
that
by
is.
8 divided by 60. Yeah.
Oh, I had it right. Okay.
Okay.
My calculator was weird and I didn't think 7.5 was right.
So this is where there's like these are textbook problems. So just because you can run, or just because a person could run an 8-minute mile does not
Mhm.
mean they can run 7.5 miles in an hour.
Right.
But for this one 8-minute mile, that's how fast they're running. Okay, so in my case, I'm running 7.5 miles per hour.
Okay.
Okay. Now you're a 6-minute runner. You're running faster. Okay. So again, 6 minutes, 1 mile. We want the ratio to be miles per hour. So that's why the six goes on the, I'm sorry, the one goes on the top. And it's 6 minutes times, well, there's 60 minutes in 1 hour. And so it becomes 1/6 divided by 60. Can you calculate that for us?
10 miles per
10.
hour.
Yeah, so your rate is 10 miles per hour. Okay, so we know we've talked about distance and we've talked about rate. We've not talked about time. What do you know about time in this problem, if anything?
Um, we know that one person runs at 8 minutes and one person runs at 6 minutes.
We've already dealt with those numbers. Those are those rates. We've already accounted for that. So again, the scenario is you're here and I'm
Mhm.
here and I'm
Mhm.
half a mile ahead of you. Later on, later, we're both at the same place.
Right.
Let's just say, for example, it takes you 10 minutes to get here. How long does it take me to get there?
Less time. If it takes me 10 minutes, then it's taking you 7 minutes, right?
Okay. Trying to say, so I'm trying to think how to do this. So the times are the same. It takes the same time. That's the key part of this.
It takes me 10 minutes to travel a longer distance. And it takes you 10 minutes to travel the same distance
No, no,
or
no.
travel,
I'm starting at a half mile ahead.
right.
So I'm
It
at,
takes
so,
you the same time to get the same place, but you started like half a mile ahead of me.
but I run slower than you do, which means I don't cover as much ground in the same amount of time.
Huh.
You run faster. So in 1 hour, you cover 10 miles. That's what 10 miles per hour means. In 1 hour, you cover 10 miles and I only cover 7.5.
7.5. Okay. That's weird to me, but okay.
The person who runs faster covers more ground.
Right.
You've seen videos where the lion catches the I don't know, the deer or something. The one's running or movies where the bad guy gets caught by the good guy because the good guy's running faster than the bad guy.
Right.
That only happens because you have a faster rate. When you're late to something, you drive faster. Well, you do stuff faster
Yeah.
to catch up. Okay, let's now dive into the D equals RT part of this because that's really what matters here. Okay, so let's talk about you. Okay, do you
Okay.
know how far you've gone? Do you know the distance?
No.
No, you don't know that. So that's D. Do you know your rate?
10.
Good. Do you know your time?
X.
We'll call it T. We'll use T.
T.
Okay, good. All right. How about so that's D1, call it distance one. And so now how about me? That's distance equals rate times time. How
Right.
far did I go?
Um, wouldn't it be D1 minus 0.5?
Yes. Whatever the total distances that you went, I went half a mile less. What is my rate?
7.5.
Okay. And how much time?
T2?
Same time. Same
Same
time.
time, right? T.
Yeah. So that's the key to this problem because you now have two equations and
And
two
two
unknowns.
variables.
And so if you call this T1 and T2, that won't work. And you'll never, you'll go in circles with
Right.
that. So I'm asking you to accept that assumption for the moment, but I'll try to give you more explanation later on that.
Okay.
But to solve this, you have a number of methods at your disposal. You have substitution, which is the main one you're going to use. So you're going to put that 10t in for D1.
Right.
So 10t minus 0.5 equals 7.5t. Subtract the 7.5t from both sides. Add the 0.5. So you have
Right.
2.5t equals 0.5. Divide both sides by 2.5. And t equals 1/5. Okay.
Okay.
But what are the units of time? And to answer that, you have to think about, well, what are the units of the rate? What was the rate in?
Miles per hour.
Yeah. So this is in hours. But you never tell someone, hey, I'll see you in 1/5 hours. At least I hope you don't.
I don't know. That's
Okay.
weird.
That's weird, right? So what do you convert hours to? What's a more meaningful unit than hours?
Minutes?
Minutes. So in 1 hour, there are 60 minutes. And you can
And
convert,
it would be something like 60 over 5, which is like
yeah,
12.
12 minutes.
Huh. Okay. So we have to change it from minutes to hours, do the whole problem, and then change it back to minutes.
Yes. The classic mistake here is to not change to hours. So in these problems, you generally want your time to always be in hours, and you always want your rate to be in miles per hour or the metric equivalent. But I think most of these are miles per hour problems.
Hmm. Okay. What about problems that are like meters per second?
Same thing. You want to try and keep them in meters per second.
Okay.
The rate really dictates what the time should be in. Whatever the rate is in, the time is in general.
Okay. Okay.
So we've done a problem where we solve for time, solve for rate, and then distance. We could do 28. Let me see what else you got here. Okay, we need to do this last type of problem. So we're going to go to 35 here. There's 3 types of problems. We have not covered all the variations on those problems, but we should use the last 10 minutes plus here, 11 minutes to figure this out. Okay, so I call these work problems.
Work
And
problems?
work problems. It's like you can paint a
Oh, like
room
in
and,
physics.
well, not that type of work. Not that type. These are more like job estimation problems. So it's like if you can paint a room in a certain amount of time and I can paint a room in a certain amount of time, then together we should be able to paint the room in a certain amount of time.
Hmm.
So that's what I mean by work problems, but really they're more like job job together problems. That doesn't even sound right, but that's all I can come up with at the moment. Okay, now these have a shortcut that I want to show you,
Okay.
and then this always works. So the formula is 1 over, oops, sorry, the technology problem. 1 over the time for person 1 plus 1 over the time for person 2
Hmm.
equals 1 over the time together. And
Okay.
we're gonna see that work here in this problem. So this always works. Okay, so you can think of it as the pipe is the person. The pipe can fill a tank in 4 hours. So 1 over 4 plus another pipe can fill the tank in 6 hours. That's 1 over 6. And we want to know how long it will take if both pipes are used together. We'll make that our variable.
Okay.
Okay, so on the left here, you need to combine these fractions by making a common denominator of 24. So we do that by multiplying, or actually, I guess we could do 12. Maybe we'll do 12. You do that by multiplying the 4 by 3 and 3.
Hmm. And
So
you
that's
would
3.
multiply the 1, 6 by 2 and 2.
Okay. So this equals 1 over t. Okay, so so this is 5 over 12 equals 1 over t. And this is one of those like shortcuts in the SAT. The answer is that t is the reciprocal of the left side, 12 over 5. But if you don't like that, you can cross multiply here. 5 times t equals 1 times 12. 5t equals 12, divide by 5, and you get the same thing.
Yeah.
Okay, so but we did one problem here, but this thing I showed you always works. Okay. Now let's talk about reality. So if you were going to paint a room, okay, and let's say you could actually do it in what do we say, or 4 hours, okay, which is a long time. And so let's imagine it's a big room.
Okay.
Or you're doing the ceilings and just, it's a lot. You're actually doing a lot there. I mean,
Right.
I'm in a 10 by 11 room, and I don't think it would take that long. Uh,
You have to
and
paint
if
the
you had a,
floors, the ceiling, the walls,
yeah,
everything.
right, yeah, but so and if if you had a friend who was like, yeah, I just did my room last week and it took 6 hours. Okay,
Okay.
um, what really happens when 2 people work together? Do you think that they are always efficient, inefficient?
Um, I think sometimes I think it depends on what you're doing.
I agree.
But if you're working on someone for painting a room, then it would take less time, right?
That's reasonable, right? You paint that wall, I paint that wall. Okay.
Right.
But what if we're like baking cookies and we both need the same oven or the same mixer?
It would take longer because we're trying to use the same ingredients,
Right.
same
Right. So there's an assumption here that there's you can both be working together efficiently. And
efficiently.
and in real life, this does happen, but doesn't always happen. You've heard things like greater than the sum of its parts, or maybe the word like synergy.
Right.
And that only applies when you're able to like not get in each other's way. And
Right. Yeah.
you can all be, you know, uh you've seen that, you've probably seen those things on social media where they pull the chair out from under everyone in the circle, and nobody's falling to the ground because everybody's carrying each other's weight.
Right. Yeah. Those are funny.
Yeah, but it only works because everybody's working together instead of against each other.
Right.
All right. Okay. Let's look at 36. Another problem here. Kind of same deal. Little wrinkle in it, but Lolita and Doug working together. That's important here. Together can paint a shed in 3 hours and 20 minutes. Okay. If Doug can paint the shed by himself in 10 hours, and you might ask yourself, well, why would they do it together if Doug already painted it? But these are the math
Right.
problems we have. Maybe they didn't like the color. How long would it take Lolita to paint the shed by herself?
So she wants to repaint the paint he just painted.
I don't know, but that's maybe you've been in a situation where you do a job and you're like, we got to redo it. Nevertheless, here the formula here is 1 over the time it takes Lolita plus 1 over the time it takes Doug, and these are individually, equals 1 over the time it takes them to do it together. This is your key to success.
Right.
Okay. Now the time together is 3 hours and 20 minutes. You cannot write 3 hours and 20 minutes in your denominator. You must convert the minutes to
Hours.
hours. So it's really 3 plus 20 over 60, which is 3 plus 1/3, or 3 1/3, or what I would like to see is 10 over 9.
Okay.
Okay. Because you want all your units to be the same. You don't want to be a mixture. You don't want to be mixing the units here. So now Doug can do it in 10 hours. All right. There's 10
Yeah.
hours. And we're trying to find out how long does Lolita take. So we'll put the variable there for T. Okay. So on the
Okay.
right here, you can just flip this 1 over A over B is always B over A. You can just flip that fraction on the bottom.
So it would be 9/10, which equals the same. Or yeah.
Like
Yeah.
that. Yep. So
And
now
then
go ahead.
you can multiply each side by 10.
I would clear this number because this is a number and not a variable expression. I would clear it
Right.
and move to the other side. So you get 1 over T equals 8 over 10.
Okay. And then you would multiply by t to get rid of the t on the denominator.
Yes.
Okay.
This is not working out. Did I make a mistake here? Oh, I did. It's 10/3. I'm so sorry.
Ah,
Ah, Matthew, that's bad. I apologize. All right.
I didn't even notice.
Yeah, I was seeing that. I was looking ahead and I was like, this doesn't work. Or the answer's not right. So here, the 8 becomes a 2. If I can get that.
Okay.
And now it does work. So,
Okay.
so this becomes, you can look at this as 1/5, or you can cross multiply and you get the 5 equals T,
T.
which is what we expected. Don't forget your units.
5 hours.
5 hours.
So it takes Louita half the time it takes Doug to paint the shed.
Right. But when they work together, it's not then further gone down by half. Okay. Like these aren't linear. And you should notice that because these aren't linear equations.
Right.
The real curves on these things, which you'll see someday when you take a probability class in college, like a real one, is like the first time you do a job, it takes a really long time. Like if you ever try to put something together from instructions first time,
Oh yeah.
second time's a little better, third time's even better. But there's kind of this like limiting, like there's always kind of this baseline time that it
Right. And
takes.
then,
Like you just can't, I mean, there's just impossible to do better than that.
yeah.
So working together, you still have there's still like some time that's always going to take. Like even if you add a third person to this problem, it doesn't go down by as much as you would think. So that's another thing to think about is like, well, how many people do we actually need to do this job? Okay. Um, how much, like if you've ever moved,